Hi, and welcome to this section of the Physics Tutor. And in this section, we're going to continue working with Gauss's law, but again, as I said before, this section we're going to be dealing with planar symmetry. So last time we did cylindrical symmetry, this time is planar symmetry. Next section will be spherical symmetry. And then we'll finally change to a different topic after that. So all of the problems here will deal with sheets of charge or sheets, any kind of thing that deals with a sheet. You're going to be dealing with a planar symmetry. So let's just dive right into it. The first problem says an infinite sheet of charge, non-conducting sheet of charge, has a surface charge density of sigma, which is in coulomb per square meter, just like it always is. Use Gauss's law to find the electric field a certain distance away from that sheet. So this is one of those things that's probably derived in your book for you, but I'm going to derive it for you here because you will probably be asked how to do it on your test. But not only that, once you understand how to do this, then you will be able to do other problems that are similar to it. So let's go ahead and do that. Okay, so let's say you have a sheet of charge. So this is what I'm drawing here, and it's infinite and it's not conducting, so there's no copper here or anything. You can kind of think of this as just being, you know, a sheet of protons or something in deep space that just happen to align themselves. I mean, it would never happen, but just pretend. Right? So you have that guy, it's positive charges, and so from symmetry you might expect the electric field to kind of radially go out from it, pointing away, right? Because it's positive. Same thing on the other side. Now don't forget, this is a sheet of charge, so you're looking at it edge on, so it's really coming out of the board. So if this is a giant sheet, infinitely long, then yeah, this electric field is pointing out of one side and pointing out of the other side, and that's the only thing that makes physical sense, right? Now the charge density that's given to you is sigma, which is the units of coulomb per square meter. And it makes sense that it's coulomb per square meter because here you have a sheet, and a sheet has a surface area, so that's why it's done that way. Now here's the deal. This is why I split the sections up the way I did, to kind of give you practice looking at certain kinds of problems, right? Even though this is a planar sheet, right? You might think, well, my Gaussian surface needs to be a box. That's your first thought, right? Because last section we had wires and we had cylinders for the Gaussian surface. In the next section we're going to have balls, so we'll use spheres for the Gaussian surface. Here you have sheets, so you might think, well, I'll use a box or some kind of linear thing like that to be the Gaussian surface. But it actually turns out, and I'll show you why in a second, that the best Gaussian surface to use for these kinds of problems is actually still a cylinder, but oriented differently. So if I want to find the field out here, the best Gaussian surface to use is actually this one, a cylinder that cuts directly perpendicular through. So you have to use your imagination a little bit. It is a cylinder, so it's a tube here, and it's cookie cutter, you know, cut right through there. The reason this is the best Gaussian surface to use is because of the following. Because all of these problems with a sheet of charge is going to have the electric field coming perpendicular out, then the flux through the side of the tube is going to be zero for all of these cases. You know, because the flux, the line is parallel, the field lines are parallel to the sides of the tube, so there's no contribution to the flux here. But because it's a uniform field, the electric field, you know, you have to kind of imagine it's extending out everywhere. The electric field goes right perpendicular through this end and also perpendicular right through that end. So it's easy to calculate